100-gram packet of chocolate nutties contains 70 grams of peanuts or more. Helen can't open up all the packets to check, as then she wouldn't be able to sell any. So she decides to use a statistical test on a sample of the packets. The null hypothesis, often called H-naught, is the thing we are trying to provide evidence against. For Helen, the null hypothesis is that the chocolate nutties are as they should be. The mean or average weight of peanuts in the packet is 70 grams. The alternative hypothesis, called H1 or HA, is what we're trying to prove. The customers have complained that the weight of peanuts is less than what it should be. So the alternative hypothesis is that the average weight of peanuts is less than 70 grams. Helen decides to use a significance level of 0.05. If the p-value is lower than this, she will reject the null hypothesis. Having decided on her hypotheses and on the significance level, Helen takes a random sample of 20 packets of chocolate nutties from her current stock of 400 packets. She melts down the chocolate nutties and weighs the peanuts from each packet. If all of the values were lower than 70 grams, with a mean of 30 grams for instance, it would be quite obvious that the bars did not have the required number of peanuts. It is very unlikely that you will get 20 packets with a mean of 30 grams if the overall mean of all the packets in the population is 70 grams. Conversely, if all the values of the 20 packets are much higher than 70 grams, it would be obvious that there were enough peanuts and that there was nothing to complain about. However, in this case, the 20 packets contain the following weights of peanuts, and the mean is 68.7 grams. This caused Helen to ask herself, does this provide enough evidence that the bars are short of peanuts, or could this result just be from luck? She asked her brother to use Excel to find the p-value for this data, comparing with a mean of 70 grams. The p-value is 0.18. Judging from the data that we have, there is an 18% chance of getting a mean as low as this or lower if there is nothing wrong with the bars. That is, if the null hypothesis is true and the mean weight of nuts is 70 grams or more. This p-value of 0.18 does not provide enough evidence to reject the null hypothesis. In this case, Helen does not have evidence to say that the bars are short of peanuts. This is a relief. The smaller the p-value is, the less likely it is that the result we got was simply a result of luck. If the p-value had turned out to be very small, we then would say that the result was significantly different from 70 grams. In general, we start by saying that the null hypothesis is true. We take a sample and get a statistic. We work out how likely it is to get a statistic like this if the null hypothesis is true. This is the p-value. If the p-value is really, really small, then our original idea must have been wrong, so we reject the null hypothesis. P is low, null must go. A small p-value indicates a significant result. The smaller the p-value is, the more evidence we have that the null hypothesis is probably wrong. If the p-value is large, then our original idea is probably correct. We do not reject the null hypothesis. This is called a non-significant result. The p-value tells us whether we have evidence from the sample that there is an effect in the population. A p-value less than 0.05 means that we have evidence of an effect. A p-value of more than 0.05 means that there is no evidence of an effect. Sometimes a significance level different from 0.05 is used, but 0.05 is the most common one. Disclaimer. This video uses plain language to get difficult ideas across. Some terminology might be viewed as incorrect by a rigorous statistician. Understanding the p-value. One of the most important...
What did you think? So, was she able to prove that there was enough peanuts in the chocolate nutties?
That's not what she was trying to prove.
What was she trying to prove?
She was trying to prove that they couldn't prove that there were
Enough peanuts in the chocolate nutties.
Yeah. So she wasn't trying to prove the number of peanuts. She was just trying to say there wasn't enough evidence to say that they were deficient.
So do you guys see how the hypothesis versus what the null hypothesis was, or what the hypothesis was, what the null hypothesis was versus what the hypothesis was, right? And then based on the test that she did, she was able to prove that there was about 70 grams of peanuts, right? Requiring her not to make a change because the p-value was 18%, right? Which is not giving her enough evidence to change or to do anything with the chocolate nutties. Yes.
What is the math that she used to go from 68.7 grams mean to the p-value of 0.18?
I don't know what statistical analysis she chose.
Okay,
I
okay.
do not know.
Okay, so there's a method. It's not just like she just put.
So every statistical analysis that you will run will give you a p-value.
Okay, so that's a okay, so that's a function of process that we choose
Correct,
to
correct.
to give us our p-value,
Correct.
as opposed to just because it almost seems like in that video, it almost seems like she's kind of
It just appeared.
yeah.
So you can use a linear regression,
Okay.
you can use a t-test, you can use an ANOVA test. All of these tests will give you a p-value.
So that's
And the p-value will tell you whether or not the statistical analysis test that was run, if it's significant.
so what's the there's obviously multiple statistical analysis programs, and do people tend to, if they don't like the output of one, will they go to a different one and see, or do they need to?
No, because the mathematical equation for statistics is the same. Okay, so the mathematical expression for a statistical analysis is the same. So what you're trying to suggest then,
Well, I
David.
know I'm not suggesting that you do it because it
No,
sounds, it sounds like a terrible practice.
No,
and
it
that
does, it does. And so yesterday when we talked about, so what happens when a researcher decides that they just want to reject the null hypothesis and go with the statistics that they were given based on the test that they ran, right? So they don't get to choose, right? If the value and the numbers that you put into the software, if it's gonna give you the same output in SPSS, it's gonna give you the same output in Excel. And the reason why is because it's the numbers, and the numbers is what's giving you the mathematical equation that's giving you the statistical analysis, which is giving you your p-value.
And then that goes back to this table in the book, that you are choosing the test based on the type of data that you're generating, because you can only run certain tests for certain types of data and certain models of experiments.
And so that's why before we went over this, that's why we went over nominal, ordinal, interval, and ratio data. Okay, it's a buildup. Because depending on how your data presents will then demonstrate what test you can run. Okay? And the test that you run, whether if it's one variable, two variables, or more, right, will change the statistical analysis. But each statistical analysis will give you a p-value, which will tell you whether or not if that statistical analysis is significant. Okay, we got there somehow or another. I see affirmations. All right, I got one more video.
Now that program that Dr. is that what we're gonna use for that? It has all the programs that you can choose from.
Has anyone ever received an email from Intellectus?
No.
No. You have?
Just cause I went on there and made an account and.
Yeah. I got a response.
Who
I
has?
had someone call me from it.
Okay, so you had to go in and create an account? Okay, cause I sent everyone's name, and so I have my username and password, but I wasn't quite clear of how you all set that up. Okay,
I did it like the first of this, I was in the unknown, and I was like, what?
so we're actually gonna go over it today. All right, so one more example of p-values and confidence levels, okay?
Hey, welcome to Sketchy EVM. I'm your host, Anthony Crocco, and today we're talking about P with confidence intervals. So what is it that I'm yearning for when I read research? I guess it's the truth. The problem is that research is not likely to lead us to the truth. It's sort of like looking for unicorns. You're not going to find one. What research does give us is a best guess or estimate of what the truth is. A problem with any estimate is really how precise it is. You may hear terms like statistical significance, or confidence, or uncertainty, or precision. Researchers will use two common techniques to describe how precise the results are. The first is confidence intervals, and the second are p-values. Let's talk about confidence intervals first. researchers will often give us a point estimate for their results. This is kind of their best guess as to what the truth is. Around this point estimate, we have a confidence interval. Well, what does this mean? Well, the confidence interval gives us a range between which there's a high probability that the truth lies. The narrower the confidence interval, the more certain we are that results are close to that point estimate. There's a couple of ways that sometimes you'll see confidence intervals written. You may see it on a graph, as we see here. In this case, the point estimate is 7, and the confidence interval is between 5 and 9. If we knew this to be a 95% confidence interval, you may also see it written as 7, with a 95% confidence interval of 5 to 9. In other words, our best guess for the truth is 7, and there's a 95% chance that the truth lies somewhere between 5 and 9. It also means that there's a 5% chance that the truth is less than 5 or more than 9. I'm guessing you may have seen something called a normal curve before, or a normal distribution. These bell-shaped curves usually have a mean, median, and mode in the middle where it's the tallest, and then standard deviations on either side, with the first standard deviations including 67% of the data, and the second standard deviations including 95% of the data. It's easy to think that these two concepts, the confidence interval and the normal curve, are the same thing, and in fact they're not. They are related, however, which we'll see below. You may be wondering what sort of factors impact the width of confidence intervals, and how does that work? Well, let's answer that. Classically, we talk about 3 things affecting the width of a confidence interval. The first is how much confidence you're actually looking for. The second is the size of the study. And the third is the standard deviation of the data set. Let's look first at the percentage or level of confidence that we want. Arbitrarily, we generally pick 95% confidence, which means we're happy to accept a 5% chance that we're wrong and that the truth lies outside of this range. If we wanted to, we could set the confidence interval at 90%, meaning that we would be willing to accept a 10% chance of being wrong. In this case, the confidence interval would be narrower. However, if we wanted to be more precise and have a 99% confidence interval, that interval would have to be much wider, so that there's only a 1% chance that the truth is outside of it. The second thing that affects the width of a confidence interval is the size of the study. Let's imagine 2 different studies. In the first study, there are 10 participants, and their results fall into a normal distribution. The second study, which also fits a normal distribution pattern, has many, many more participants. Both these studies have similar mean, median, and modes. If I were to ask you which study results you trusted more, you'd probably say that you're less confident in the study that has fewer numbers. This would be reflected by a point estimate that has a wide confidence interval. On the other hand, the study that has more participants, you'd say, well, yeah, I'm more confident with these results. This is reflected in a confidence interval that's actually narrower. The more participants in the study, the more precise the results, the narrower the confidence interval. A third thing that affects the width of a confidence interval is the standard deviation of the data set. Imagine a study where the results were all over the place. Although they fit into a normal distribution, the distribution is quite wide. Now imagine another study where the results are pretty close together. In the first example, the standard deviation is quite large, and as you can see in the second example, the standard deviation is much smaller. All other things being equal, this is going to result in a much larger confidence interval around the point estimate in the first example, and a much narrower confidence interval around the point estimate in the second example. So these are the major influencers of the size of a confidence interval: the percentage you pick, the size of the study, and the standard deviation. Now, what about the whole concept of not significant? When are results not going to be significant? Well, in simple terms, you want to see if the confidence interval includes or crosses the line of no significance. In most studies, this non-significant value is 0. Sometimes the non-significant value is 1, and this is usually seen in cases where we're looking at relative risk or ratios. Let's see what this might look like graphically. In this study, we're trying to distinguish between this working or that working. Our line of no significance is going to be 0 in the middle. In our first example, the point estimate shows that that works, and the entire confidence interval is on that side of the line of no significance. It does not cross the line of no significance, and therefore is considered a significant result. In the second case, the point estimate is also showing that that works, but the confidence interval does cross the line of no significance. In this case, we would say that the results are not significant. Alright, so I hope you're confident with your knowledge of confidence intervals. Let's talk about p-values now. P-values are another way that researchers can describe precision of the results. And you've probably seen this before in a research paper that says this is better than that, p equals 0.05. Well, what on earth does this mean? What the p-value tells you is the results that the researchers found occurred by chance and not as a reflection of the truth. A common mistake that I've made is thinking that a p-value of 0.05 means that there's a 95% chance that the results are true. This is in fact not the case. The p-value really only tells us that there's a 5% probability that the results we're seeing could have occurred by chance alone. It's a subtle difference, but sort of similar to what we see when we talk about the false positive rate and true positive rate with diagnostic tests. Much like the confidence intervals, your p-value can be set arbitrarily at any level. Classically, we use a p-value of 0.05, but sometimes this can be 0.01. The smaller the p-value, the more precise the results. So at the end of the day, what do I want you to remember about all of this? Well, first of all, I think we need to remember that research doesn't give us the truth. It gives us an estimation of the truth. And as such, we need ways to describe how precise these results are. And this is where p-values and confidence intervals help out. The confidence interval does this by giving us the probability that the truth lies within a specific range. And the p-value tells us what is the probability that the results that we're seeing occurred just by chance alone. In both cases, we can actually choose how precise we want our results to be, and this can change whether the results are deemed significant or not. I hope you enjoyed this rather long, sketchy EBM. Please do take the time to evaluate, and as always, remember to draw your own conclusions.
Helpful or not?
Yeah, very much.
So let's end where we began. Catherine, we were talking about p-values and having some question about whether or not if the p-value and your understanding of p-value when it comes to statistics. Then I helped transform what we talked about yesterday to what we talked about right now today, you having some additional clarity on understanding p-values.
Yes.
Yes. How many of you, by show of hands, and so hopefully my significance level is less than 5. How many of you?
I'm going for 0.
0. I don't know. I need to know how many of you have a clear understanding of p-values now than you did yesterday. Oh, good. 0. So what we're going to do now is we're going to break you guys down in groups. It doesn't matter to me what groups that you guys break down into. But we're going to talk about, I want to have you all talk about this article. Highlight and ring true and really dig deep into this article about the things that we just talked about. Probability, level of significance, confidence level. And really break down and interpret whether or not if you can ascertain, based on this research, of depression causing or being a risk factor for coronary artery disease in women, right? So that really is the question. Can we statistically say that depression is a risk factor for coronary artery disease in women? Okay? What questions do you have?
How long do you want us to take to
I was just about to say that. So let's do a 20-minute discussion, then we'll take a 15-minute break, and then we'll come back and discuss the discussion. Okay? All right? And then after that, we'll move into intellectus.